Now, given a language which is variables, functions, and relations, we know what are them, and because we have the logical symbols, they are same in every theory, and variables actually change with every theory. So we also need to put them here. All right. So we have some logical symbols, which is common, equality, and all of these things, and and functions. We know we will use the symbol f for them, and relations we will use r, f, g, r1, r2, anything. We just need to know if they are relations or they are functions, or what is the n, how many inputs will they take or something. And all right, now what we need is what we need what we need is some semantics. We need to assign some truth valuation to our well formed formulas. Now, how do we do that? We don't need to assign the truth. We don't need the full data, obviously. Previously, we have assigned only that valuation on the atomic forms, and that has given us a unique valuation on all well formed formulae. So, what we will do, which is we will just define what is called a structure. Structure will have four things. For we will have a sort of set, which is a collection of objects. We have not defined set theory yet, so it is just a meta collection of objects. We will call our structure M, and that will contain some collection of objects M. This will be like, let's say, set with objects. What can we call them? S1, S2, countable, uncountable. We don't really have any notions of. It can be really literally anything actually, and that uncountable objects gives us a problem of we can't reach them in a finite time. So I think that becomes a problem afterwards. So that we have to decide after constructing set theory and talking about um, infinite sets. Now it has objects. Now what we will do, we will assign variables. For each variable we will assign some object, which we will write as am of x. So that is what I previously interpreted as each x plus 5 equal to 6. If I assign the object variable x the object 1, then this statement will be true. So we need to for each functions f, we will have a actual function from this set s m. So this will be actual function on the set x cross x cross x for n number times, which is the NRE function, and it will give you an actual output. And for every relation you want this would be a function from n times to sm. This would be relation would be just a function from so it will assign some truth values to n tuple of objects. uh, um, x less than y would be given a truth value depending on the what variables x and y, what objects x and y are attached. So it'll be something like n tuples to true and false. So on the right hand side, this is the data. On the right hand side, these are the data we have been given with the structure. This FMs, this RMs, and this AM. Now, the theory is the language contains all these variable selection function. This is language, and these are parts of the structured data. Now, given this data of the structure, we can actually do more with them. We can define for each term. So every term would look something like T1 0 T2, or some relation T1 Tn, or something like for all x. Oh shit, I'm doing terms. Sorry about that. Terms look like variables and f T1 Tn. These are terms. For each term, we will assign an object. So variables are already assigned an object. Using that information, what is the symbol again? And this will be assigned. So this was a string before in language. Was just in language. Because we have attached f with some actual function which takes actual objects to some another object, and T1 is already assigned an object, so we will just assign f of those things, the object that is assigned to that, because every object is already assigned something. So for example, if fxy is a term and x is assigned a1, y is assigned a2, the objects in sm, and these are variables in our language, then automatically fxy, this term, is assigned the object wherever f maps these things to. So f can map a to a2 and a2 back to a2. Then okay, it would need pairs of objects. A1 a2 would be mapped onto say a2. Then f, this has to be mapped to a2 by this construction, because it would be f of this is fm, this would be fm of the way this thing. So this will be a1, this will be a2, and this will be mapped to a2. This is by definition of what we are mapping f to. So there is already an information of f is already assigned fm, which is inside the information of the structure. And what will this help in? A concrete example would be something like functions. What are functions? Addition is a function. So 5 plus 7, these are objects. So our sort of all objects, this sm, would be something like 0, 1, 2, and our variables are xy, and x plus y is equal to some there's a zero array function which maps to 0. Then this would be just a string. Using this actual function which we have defined here, 1 plus 2, which is an actual function, plus which is coming, where it is coming from we will discuss. That is part of the structure, this addition. And if I assign x to the number 1, y to the number 2, then x plus y would be this string. This term would be attached to the number 3 by our construction of that plus. And we also want to assign x plus y is equal to 0 the valuation false. So for every well-formed formula, so every term is assigned a object, and every well-formed formula are assigned a truth value. That is how they are different, and that is where functions and relations are actually different. Term is made up of functions, and a relation is made up of well-formed formulas can be made up of relations or for all x. They are different in that sense. So a structure would actually contain four pieces of information. It will assign it will give me some objects 0 1 to 3 or some other thing, and it will give me some n array functions which are actually functions on the set theoretic sort of. We know what set theoretic functions look like. It will actually look like them. They're not strings. They are actually, they will take some objects and map it to some other object, and a relation which will take some object and map it to some truth and false. And for every variable in our theory, it will map to some object in our collection. So we have already chosen what our structure is. If you are solving the equation x plus 5 is equal to 6, we have to choose some structure. If we choose x mapping to 1, then everything is set already. If we choose everything is set, and that x plus 5 is equal to 6, that equation, that well-formed formula will be assigned the value for true. If x is 1, assign the value 1. So that is what it would look like. Up to the information of how to assign objects to terms. Now we have to assign some valuation to each well-formed formula. That becomes a bit tricky when talking about for all or there exist. But giving T1 validity to the valuation is very simple. If I assign the valuation, if I assign some object to T1, which is a term, we have assigned object beforehand, and T2 some another object A of T2. If they are the same object, this equality is in meta sense. We know which objects are the same. Then we will assign the valuation true to T1 is equal to T2, and false otherwise. That is easy to define. There will be no problem with that. Again, we have to indirectly define what are the objects, and if they're the same. Yes. Knowing two objects are the same is another problem, might cause another problem. But other than that, if we know all that, then this is fine. Assigning truth values to P box Q or not P are using using truth tables of the logical connectors. And again, relations use the same thing. Relations are already giving some valuation on what input they are taking in. If I give some our language relation, so some language relation string, then it will assign that string, which is a well-formed formula, some valuation which is preserves the structure of the what relation R is mapped onto, what function R is mapped onto. The truth value is given by that. So that would mean something like, if there is a relation in our language less than, and I have a well-formed formula 5 less than 6, then if I assign the less than relation to the actual relation which is in natural numbers, we have not defined arithmetic yet, but this is a vague example. Then 5 symbol here, this 5 zero array function and zero array function. Let's say variables something. Let's say x less than y, and x is attached with 5, y is attached with 6. Then x less than y would be attached with some truth value, where in this case it will be true because we have defined what less than is inside here. And 5 less than 6 is actually true here in our, in the sense of, um, in the structure itself. So, are we doing all the game in the structure itself, or why do we need a theory if we know everything already? We need a theory to do logic, I guess. We need to do proofs. Um, will depend on the theory to develop a lot of stuff. We might not be able to know, and that is why we will define use it as a theory to define set theory. But yeah, that is a pondering question. We might not be able to decide on some problem. The problem might not be decidable because there might be really the objects, several objects might not be a set. It might be a really large some collection. We don't know. And okay, what we have left to do is assign every for all x p some truth value, and there exists p some truth value. We will do that next.